Here we go. More astronomy lectures. This time, we'll be talking about the birth of stars and like where it happens, how it kind of happens. Actually, kind of breaking this chapter up into two parts. So this is part one. If you're following along with the text, if you're not following along the text, then it doesn't really matter. The next part is about what tends to come along with stars being born, or planets. Lots of pretty pictures in this area because it turns out the stars are born in nebula. So this is part of the Carina Nebula, which I guess isn't constellation Carina. It's just big old dust clouds, gas and dust, but it's the dust that eventually gets dense enough where it starts to get dark even though there's light being shined on it. So the really, really dense areas are sort of the darkest areas, and those also happen to be where stars tend to form. So that dust gets dense enough that we can start the process of getting towards a star. So if you remember the really dense clouds of interstellar dust, we call them molecular clouds. Sometimes you might see them called stellar nurseries because they're the place where stars are born. Some more cool pictures. I think I showed you the pillars of creation before. That was a painting. This is actually a photograph or a collection of many photographs put together to build this image. And this is just another nebula, part of a nebula, part of the Eagle Nebula. It's a bunch of gas and dust, quite large. The tallest pillar is about a light year across, or a light year long. And so there's possibly star formation happening inside of the really dark areas in the image on the left. But also what's happening in this image is that sort of above where we can see, or above where the photo ends, there are some really young, bright, hot stars. And so the tops of these pillars, particularly the left pillar there, where you get a close-up on this side, is sort of glowing because it's being heated by the energy given off by those young stars there. Just really cool pictures. Alright, so down to some more specific information about these molecular clouds, again sometimes called stellar nurseries. I told you about them a bit in the last lecture, possibly the lecture before that, but just to remind you, they're rather cold, 10 to 20 Kelvin, which is, just above absolute zero. Really quite cold. I don't know exactly, off the top of my head I'm trying to think, that's like, it's a few hundred degrees below zero in Fahrenheit. Very good. The amount of mass that's in these clouds can range from like thousands to millions of solar masses, or millions of times the mass of our sun. And yeah, pretty big. They can be up to 1,000 light years across. This is another image of a nebula, and so the darker regions in there are like the molecular clouds. So if we're thinking about these molecular clouds, right, fairly dense regions of the interstellar medium, of interstellar dust in particular, to remind you that when they're dense enough, they sort of block out any energy coming in. So they block out visible light, they block out ultraviolet light, and so inside, things are sort of allowed to congeal more and more, they're clumped together more and more. Something that can happen is that you get these clumps start to form that are somewhere like 50 to 500 times the mass of our sun, those clumps, and within any clump, you might have, or you have the possibility of even denser areas forming within there. So gravity is just kind of collecting all this stuff together, attracting all the mass to each other, so you form these sort of clumps, and then within the clumps it's even denser, and you can form these cores. The cores then are sort of the early stages of a star developing, sometimes called a stellar embryo. Oh yeah, like I was mentioning, within these clouds the temperature is really low, and even though gravity is crushing things together, and you're getting energy put in by all this stuff collapsing, the temperature stays relatively low, and so the pressure of that material pushing against each other, kind of pushing out, stays pretty low too. So we're sort of allow gravity to keep crushing things down, pulling stuff in. So I've showed you the Orion Nebula before, at least once. If you recall, the Orion Nebula is sort of on the sword hanging down from Orion's belt. So you can kind of make it out a little bit there in that image, but the entire constellation of Orion is within a much larger cloud of sort of interstellar gas and dust. And we get these really, really large clouds. They're sort of collections of multiple clouds almost in a way, almost like a complex, cloud complex. And it turns out that the Orion molecular cloud complex is larger than the constellation. And you don't see all of that stuff, again, because it's really cold in general, and so it's not really giving off visible light. So in the visible spectrum, we don't see that. But if you look in, say, the infrared, then anything that's giving off heat or infrared radiation, then we will see. So it turns out in infrared, you can see a lot more of this complex, right? It's larger than the whole constellation there. And some of the hottest regions in the infrared are right near the nebula, just because the new stars in that area of the cloud are heating all the gas around it, so that gas ends up giving off a lot of infrared radiation. Comparably, the stars that are in the nebula area are rather young, like a few 100,000 to 1,000,000 years old, which is quite young in terms of the life of a star, or cosmic sort of time scales. Before we get further along in looking at the process of a star forming, think for a second about what it is that causes a star to form, or what triggers star formation. This is still sort of an open question, but one way that a star can kind of get going, or like the pre-stages of a star gets kicked off, we think is by this process that we call triggered star formation. And that happens when another star that's already there, it's really bright, giving off a lot of energy. It's sort of putting out waves of energy that are then traveling through the molecular cloud that it's near. And those waves are sort of like sound waves almost, where the wave, as it travels, it compresses areas, and then those areas expand, and then compresses further areas along, and those expand, and compresses further along, and those expand. And so these are what we call compression waves, or technical term would be longitudinal waves. And then in that compression, that's when you sort of get enough of the dust being kind of pushed together and squeezed together that you sort of tip over the point where gravity can really start to pull more and more stuff together. Right? So you have this kind of loosish cloud of dust and gas, and along comes this wave where it compresses areas as it goes along. And so that's enough to then sort of like trigger the rest of the collapse to continue. So the animation there of like a speaker and what it does to the air molecules. If you didn't know, sound is just a movement of air molecules, and it's this compression wave. Nicely enough though, all waves have very similar properties, and so the image of the speaker compressing the air molecules outside of it, and that compression sort of traveling outward, is very similar to the star putting out energy. And it puts out energy, and that energy travels in these sort of waves outward. So for sure, all stars can't be triggered in their formation by other stars, because it just kind of begs the question of what about how did the first stars start forming? Or like the first generation of stars, you might call them. Well, these are still sort of open questions. Maybe there are other cosmic events, maybe it's just random accumulation of gas. But this is at least one way that we're pretty sure star formation gets sort of kicked off. So here we sort of have a really simple breakdown of the process of how you go from that dense core in a molecular cloud to what we call a protostar. So in A, we start out with this pretty dense core that's still rather large, 5,000 astronomical units. It's still pretty large. If you just look at the diameter of our solar system, it's about 100 AU. So that's 50 times the size of our solar system. Pretty big. Well, now there's sort of enough material there where it's just going to keep pulling more and more material in. And so you get to this phase where you kind of have this protostar forming, and a bunch of material forms into the center where the star will end up being. But just due to sort of random motion of all the stuff that makes up the gas, these things are almost always spinning. Right? There's this rotational motion going on as all this gas and dust is collapsing in, it's everything is rotating. And what that ends up doing is forming a sort of disk around the central denser area. And so then you get sort of enough material collapsing in where gravity, just the contraction of all that material pushing in on itself, is going to start heating things up. So it starts to get quite warm. It's not hot enough to start fusing hydrogen yet, like do what our sun's doing yet, or do what a regular star is doing yet, but there is heat being generated inside of the core of these protostars, and that heat wants to flow outwards. The thing is, with the disk being there, it sort of blocks heat from escaping very easily out like the equator and around the sides of the star. So instead of flowing there, it much easier will flow out of like the poles. Right? So the star is spinning around like this. There's less blocking the way of the heat going up and down here, out of the poles. So you still have dust that's sort of collapsing in and coming in, but now we have this energy flowing out of the poles as well. So the whole process sort of ends or comes to a new stage when that collapse has happened enough where you increase the density of the interior of this protostar enough, where the pressure has gone up enough and the temperature goes up enough to finally start fusing protons together. So that's where we get to that nuclear fusion, the proton-proton chain that is happening in our sun, and it happens in all stars once they reach this stage, and this is now what we call the star. Still has quite a large disk of this material, it's dust and gas, that didn't all fall into the star. It formed into that sort of disk around it, and we'll see a bit later that that's essentially where the planets get formed from. And we saw that a while back when I told you about the formation of our solar system. Right? Stars in general seem to follow a pretty similar process. Here we have a couple of animations showing this process. I think in the animation on the left, we're starting out with like that core inside of a clump in a molecular cloud. It's collapsing down, right, until we get to this sort of protostar stage where it's spinning around, it's collecting more stuff, and that disk forms around the outside, and the interior is getting heated up enough in that protostar by the crushing of gravity that heat wants to flow out, and it ends up flowing out the poles. On the right here is just a picture of this process happening, and it's a little bit more clear in this picture on the right that this all generally is happening within a larger cloud. So the protostar is forming in there, it's shooting out this energy out of the poles, and sort of still sucking in maybe more gas. And it can be the case that more of the cloud that's surrounding this protostar forming falls in too, which can sort of keep adding more material, but usually it sort of clears out its own little space in there. In the animation on the left, it's a little bit deceptive because for the most part, you're not going to see like the far stars behind this protostar when it's forming. Right? It's still within a cloud of gas and dust, a molecular cloud. So that process of having the whole protostar spinning around and energy not being able to go out the disk, up the sides, and having to shoot out the poles, can make for some pretty cool looking pictures. So here is a series of images of one protostar in the process of forming, and it's shooting energy out of its poles. In the lower end of the images here, you have this sort of two-cup looking thing, chalice looking thing, and in the center of that, in the darkest area, is actually where the protostar is. So you don't actually see the protostar because it's still surrounded by this dense disk of dust. But we do see the heat that's coming out of that protostar heating up some areas in the disk above it and below it, and besides that, just shooting this energy, and then occasionally like chunks and like clumps of material get shot out of the poles as well. So like a lot of stuff in astronomy, the jet, that material being shot out of the pole, is given a name, and it was named after some of the people who first observed it, or I think first observed it, Herbig-Haro. I think that's how you would say it. So these jets are called Herbig-Haro Objects. They can make for some really cool images, so I got a couple of those. So this is more images of protostars during their formation, and spewing out energy and some material out of their poles. In the upper left, I believe, is actually just one jet, so like coming out of one side of a protostar, and you don't see the protostar again because it's covered, or it's still surrounded in that dense disk of gas. But on the far left, it is sort of heating it up, where that gas, that disk is being illuminated somehow. So the white area on the left is sort of where the protostar is, and this jet is coming out to the right. And it's not really going straight in that image, and the book mentions something about maybe the protostar is like wobbling kind of weirdly as it's spinning around, so it creates this sort of odd-looking jet coming out. As that energy sort of runs into the gas and dust that's still around there, it heats that stuff up, and then that stuff will glow and give off light, maybe visible light, maybe infrared light. The next image on the left there is two of these jets. I think HH stands for the Herbig-Haro. It's a little bit confusing because I think a Herbig-Haro object is just one of the jets. And so in that image there's actually two, but those are jets that are coming from sort of either side of the protostar. Right? One's coming out this side, one's coming out that side, because the protostar is spinning around this way, and these are the poles. And again, that energy is crashing into the material in that cloud surrounding it, like not the disk area. This is still the larger molecular cloud that this whole formation is happening in. And so it smashes into that stuff and heats it up, and that stuff glows. This last image here, I just think is so cool. I don't know. It just looks awesome. But again, more of these jets, right? So the protostar is inside of that dark area, sort of where the one kind of cloud looks like it's coming down and the other one's coming in, and the jets are spewing out of either side. Yeah, so cool. These are some more images of protostars with disks still around them, and some of them are at different angles, right? So you might actually see the star directly a bit. I think in the very bottom left one, we're probably looking face on to the disk, right? So the disk is like here, and the protostar is in the center of it, so we can actually see the protostar directly, versus like the bottom right one here, where the disk is something like this, and the protostar is in the center of that, so we don't see the protostar, because this dark band of the dust disk that's still around the protostar. Go into a little bit more detail about that sort of final stages with the protostar. When it gets to the point where it's actually a star, that's when nuclear fusion is actually starting. So those protostars, like I said, are quite large. Stuff is still kind of collapsing in, and they're pretty cool. And even though stuff is getting denser, it's generally not dense enough to really block the flow of heat out of the core of that protostar. And so for a while, stuff is collapsing, but heat is able to flow out. So gravity is going to continue collapsing that stuff, right? Adding more energy, crushing things down, and more energy to the interior of that protostar, heats it up, and that heat wants to flow out. It will generally flow out of the poles, but as long as it's not still too dense, that heat is able to get out, and we get those jets. Eventually, that protostar is collapsing enough where the whole size of it kind of shrinks down, and basically a smaller thing just is going to be able to put off less light, so the luminosity of it drops down a little bit. And once it gets to that sort of area where it's shrinking down in size, the density is going up enough where the heat that's being generated by all the crushing down of the interior isn't able to flow out very easily anymore. So if the heat is being trapped in there, then everything is going to get hotter, right? The temperature starts to go up inside. And once you sort of get to that phase, it's only a matter of time until the temperature gets high enough, like about 10 million degrees Kelvin, which is around the temperature we need for fusion to begin. Fusion begins, that's when we build a star. Give you a rough timeline of how long some of this stuff takes. So remember, we went from a core forming inside of a clump inside of a molecular cloud. Right? But once you get to the phase of that sort of core stage, it's something in the span of thousands of years until that core will generally get to this protostar phase. So how long does it take then for this protostar to get to be a star? Well, that can range quite a bit, right? So it depends on the mass. If there's a lot of mass there, then overall there's a lot more gravitational attraction, and so this process tends to go a bit faster. So when you have something like 2 to 200 times the mass of our sun, then that process can take anywhere from like 1,000,000 all the way down to only a few thousand years. A few thousand years is very quick on cosmic timescales. If you have sort of a medium size protostar, so about the mass of our sun, that then takes about on the order of millions of years. When you have a really small protostar, less than maybe half the mass of our sun, that can take tens of millions of years for that collapse to happen. So much less mass around, the amount that all this stuff is pulling on each other due to gravity is a lot less overall. Less mass, less gravitational attraction. So I hope you liked HR diagrams, because those are going to keep coming back. And in this case, we can visualize the evolution of a protostar to a star as a sort of like path or a track on the HR diagram. Because as it goes through this process of collapse and spewing jets and fusion, ignition, its temperature overall and the amount of energy it's giving off, its luminosity is changing. If you remember, HR diagrams are temperature versus luminosity. So as those change, you can sort of imagine a point where a protostar has a certain temperature and luminosity, and as it evolves, both of those things change and sort of starts to move through the HR diagram. Remind you a little bit more about HR diagrams. Right? There's one on the left there. Again, it's plotting temperature increasing from right to left, so the hottest stuff on the left, the coolest stuff on the right, and then luminosity, right? Energy output. So lowest energy output down here, highest all the way up here. And remember, most of the stars that we see, we observe, fall on that sort of diagonal that goes from the upper left to the bottom right. The upper left being really hot, really bright stars, all the way down to bottom right being really cool, really dim stars. We call that diagonal the main sequence. The star was on that diagonal. This is what we call a main sequence. And hopefully you remember that what connected all these main sequence stars is that they're all doing the same thing our sun is doing to produce energy. Right? Fusing protons together and through the proton-proton chain making helium. The other chart I have on here is also an HR diagram. It's just a bit simpler, only sort of plotting some main sequence stars and then drawing a line that kind of approximates where all those stars fall. So if a star falls on that line, that's what we consider to be main sequence. Protostars, when we plot them, they're generally going to be up and to the right somewhere here, and as they move towards becoming a star, and they get to nuclear fusion, that point sort of moves down. Generally it's going to get a bit dimmer and then get a bit hotter until it finally hits the main sequence star. So we're going to look at a few different protostars and how their paths look as they go towards the main sequence. Later on, we're actually going to look at the end stages of a star's life, and that also we're going to visualize on the HR diagram, and that's generally like a star is on the main sequence and runs out of protons to fuse together really easily, and it starts to move back away from the main sequence. But that's later. For now, we're just looking at protostars. So here again, HR diagram. That red line, what's labeled 0 age main sequence, that's the main sequence line, right? So that's where all these stars will fall if they're doing proton-proton fusion. Here we have a protostar that's about 1 solar mass, right? About the mass of our sun. And where it starts out as a protostar is at the top of that black line. And so it starts out, it's a good bit brighter and a little bit cooler than our sun, right? Because our sun is right where it's going to end up eventually on the main sequence there. So it's like anywhere from 100 to 1,000 times brighter and maybe 1,000 degrees cooler or so. And as time evolves, the numbers next to the black line are the amount of years after the protostar formed. The protostar formed 10 to the 5 or 100,000 years later. It's moved along the HR diagram to that black dot there. Right? It's gotten a lot dimmer, a little bit warmer, and then 10 to the 6th That's 1,000,000 years. That's actually 900,000 years after that first dot. It's gotten even a little bit dimmer further down here. Keep going, somewhere in the range of a few million years after it started way up here. It's gotten all this way dimmer, a little bit warmer, and then just before it hits the main sequence, it sort of brightens up a little bit again, gets a little bit hotter, and finally lands on the main sequence. That's when proton-proton fusion has started. We have a star. So it landed right there on the main sequence. So this is like a star very similar to our sun. So in the end, it ends up with a luminosity that's basically the same as our sun, one luminosity of the sun, at about 6,000 degrees Kelvin, right? Just like our sun. That's the surface temperature, 6,000. Technically our sun is like 5,800. I just rounded it, about 6,000. The one other thing on this diagram is this dotted line. Apparently, after a protostar has moved along in its evolution enough, when it passes that dotted line, that's roughly the time where that dust disk will have cleared away. For this one solar mass protostar going to star, after that disk gets cleared away, that's about when it brightens up a little bit and heats up a little bit and finally gets to nuclear fusion. So that was a protostar much like the one that formed our sun. But we could also imagine the evolution, or sometimes called the evolutionary track, because we're drawing these tracks on the HR diagram. We could imagine that for a much smaller star. So a much smaller star, say like a 10.1 the mass of our sun, it's going to start at the top of that black line. Actually, at that point, right, it's roughly similar luminosity to our sun, but a bit cooler, right, 2,000 Kelvin maybe. And then over like 1,000,000 years, it goes down on the HR diagram, meaning it gets dimmer and maybe a little bit warmer. It's like slightly going to the left, a little bit warmer. But it takes quite a long time, remember, for small mass protostars to form to stars. And so even by 10 to the 8th or 100 million years, it still may not quite have made it to the main sequence, meaning nuclear fusion still might not have happened. So that path is basically just dimmer, 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 a little bit warmer the whole time, and then eventually you probably make it to nuclear fusion, but it takes a long time. How about for a really big star? Really big star, like 100 times the mass of our sun. So you start out with a protostar that's like 100 times the mass of our sun. It's generally going to start out at the end of this black line at the top here. So already it's really bright, 10 to the 6th or like 1,000,000 times brighter than our sun, and it's about 3,000 Kelvin. So similar temperature about to where one solar mass started out. But its path looks a bit different than these other ones. These other ones mostly kind of drop down in luminosity, warmed up a little. For the really big stars, they will drop down in luminosity a bit, right? So by about 100 years, its luminosity has dropped a bit, and it's warmed up a bit, it's moved to the left. And then it just sort of gradually raises back up to a similar luminosity, around 1,000,000 times the luminosity of our sun, and just keeps warming up, getting hotter and hotter and hotter and hotter. And it takes a lot less time. So 10 to the 4 is like 10,000 years plotted for this 100 solar mass protostar to make it to the main sequence, right, where nuclear fusion starts. And then here we have the same sort of plot, but a number of other masses thrown in there, right? So we looked in more detail at the track, the evolutionary track of one solar mass protostar, of a 1/10 of a solar mass and 100 solar masses. On here we have a couple more that are in between, like 10 solar masses, 3 solar masses, half a solar mass. So just very broadly speaking, when you have like a high mass protostar, they will generally get warmer, get hotter, and dimmer for a little while, but at some point they have sort of like turn on the HR diagram and start getting brighter again and just keep getting hotter. The low mass star on the other end, or pretty low mass generally, just get a little bit warmer but kind of continue to get dimmer as they go towards the main sequence. Cool. So hopefully that made some sense, because again we're going to use a similar approach to think about the evolution of stars at the end of their life. So once they get to the main sequence, in the next chapter, not next lecture, but the lecture after, we're going to talk about sort of their time on the main sequence a bit. Right? That's where they spend most of their life, or most of their life cycle is spent on the main sequence, but eventually sort of run out of protons that they can really easily fuse together, and that proton-proton chain is no longer an option, so they have to do something else, which sort of moves them off the main sequence, or moves them back off the main sequence. Alright, well that's it for part 1 of this chapter, and so next time, talking a bit about what happens to the disks that were surrounding these protostars as they were forming. Spoiler alert, it's planets. Until then.